Good evening, everyone. I, Adya Pandey, welcome you all to today's PSPO session. Today's speaker is Mr. Mohammad Alfas, who is a Ph.D. scholar at the Department of Mechanical Engineering, IIT Delhi. His current research focuses on network-based diffusion models. Besides network science, his other interests include resource allocation and reinforcement learning models. Today, he will present his work on online heuristics approach for efficient allocation of limited COVID-19 testing kits. Over to you, Alfas.
Thank you, Adya. So let me share my screen. I hope my screen is visible. My screen is visible, right?
Yeah, it's visible.
Okay. So welcome all. So thanks, Professor Namesh Bulia, for inviting me to present in the PSPO symposium. So my topic for today's talk is online heuristic approach for efficient allocation of limited COVID-19 testing kits. So regarding my work on public systems, this talk comes under the domain of resource allocation models and controlling epidemics. As we all know, resource allocation models are critical in public systems. We need to allocate resources across the population optimally in order to achieve a welfare state. So that's the objective of public systems usually. And obviously, controlling epidemics are crucial regarding public health and all. And my major research focus is on modeling of societal spreading process using simulation models. So this is about my work on public systems, since this topic is regarding the public system, comes under the public systems PSPO symposium. So this talk is based on the paper we presented me along with Professor Shaurya Shriyam in the ICORS conference, International Conference on Operational Research and Enterprise Systems. So this is the citation that this is a citation for the paper. So coming to the topic, as we all know, India witnessed a gradual, slower increase in the initial phase, in the first wave of the COVID-19. So in this phase, the obvious solution to reduce the number of cases was test more, as we don't have any particular treatment protocol or a particular idea how to control the disease. So the only preferred method was testing, as WHO said test and test and test as much as possible. So if we test more people, we can isolate more infected people and we can reduce the spread. The idea was to flatten the curve. As the most of the epidemic models follows, we expect that eventually everyone will get infected, but to delay the infection to our total population, so that we will develop more treatment protocols, more vaccines. So in order to do that, we have to need to test more people. But the major constraints was the availability of testing kits. The number of testing kits available was very limited. So in that context, we obviously have to do optimal allocation of testing kits. And another method that actually nobody followed was pooled testing. So we usually allocate one testing kit to one person. So in pooled testing, instead of allocating one testing kit to one person, we take a sample of a group of people, and it is one testing kit is allocated to that sample. So a group of people is tested together. So based on this optimal allocation and pool testing, we have developed an allocation framework, and we experimented the model with a 5-city data set. The 5-city data set is data from major 5 Indian cities. So this is the overview of the allocation process based on the allocation framework we developed. We have historical data of the past testings and infections. And based on the historical data, we estimate the prevalence of the disease. And based on the prevalence, we use a bandit allocation model to allocate optimally across all testing kits. And then we distribute these testing kits to testing labs. And in testing labs, we do pooled testing. So that's the allocation process. So the first component of the allocation framework is prevalence estimation. So prevalence is the proportion of the population in a place that is infected by the COVID-19 or any disease at a particular time. So usually we use the metric of daily test positivity rate, or TPR, as an estimate for prevalence. So one major issue with the TPR is that, as we all know, usually people who have symptoms or people who come contact with infected people, they only go to testing. So the TPR may be an overestimate of the prevalence. So instead, but we only have the data of the tested people and how much infections are only. We only have that data. So we use an empirical bias paradigm to estimate the prevalence rate. So we can model the probability of a person getting disease as a Bernoulli distribution. A person can either get infected or not get infected. So if we consider a group of people, it will be a binomial distribution. And since we are following a bias paradigm, the parameter of the binomial distribution, that is the probability of getting a person infected, the p-value, will follow a beta distribution with the parameters alpha and beta. And we can estimate the value of alpha and beta using the past data. Here we use past 2 weeks data. And we can approximate the binomial distribution if the probability is very, very small. In the case of Poisson distribution, if we approximate the Poisson distribution, the parameter, the lambda parameter, will follow a gamma distribution. So beta binomial and gamma Poisson are two commonly used Bayesian probability distributions. So the allocation is, we use a multi-armed bandit problem. So the major concern in allocation of testing kit is where to allocate testing kits. Whether we have to allocate to the places where prevalence is high or to the places where the prevalence is low. So the usual idea or the usual intuition is to allocate the testing kits to places where the prevalence is high. But we strictly follow the prevalence rate, there will be a danger such that if we miss the places where prevalence is low, there will be high number of cases in future. So we need to have a trade-off between this exploration exploitation thing. So this exploration exploitation dilemma can be modeled using a multi-armed bandits model. So what is multi-armed bandit, or MAB in short? So in MAB there is a gambler, and the gambler needs to choose a slot machine to put money to gain maximum benefits. So there are a number of slot machines, and the gambler needs to find which is the best slot machine to put money in order to gain maximum benefits. But the gambler have one advantage is that he don't have to put all money in the one slot machine. Instead, he can put some money in a slot machine, and based on the output he received, he can update his information. So since we already use the Bayesian model of prevalence estimation, we follow a online decision process. So what we do is that we start with a simple base data, and as we go forward, we update our model, and based on that we allocate. So this is a classic reinforcement learning problem, and to solve the MAB problem, we have many models are available. A few of them are Thompson sampling, upper confidence bounds, and Gittins index. In this model, we use the two methods only, Thompson sampling and Gittins index. So in Thompson sampling, we have the parameter values as a posterior distribution since we use Bayesian method. So we randomly sample a value from most recently estimated posterior distribution for each city's prevalence rate. Then the city which have the largest random sampled value will get one as testing kit. And we continue this process until every testing kit is expensed. And in Gittins index, the Gittins index has an equation, as we can see, lambda is equal to alpha divided by alpha plus beta. So in this equation, we have to find out the value of lambda. Lambda is the Gittins index value. So it's a equation need to be solved using any numerical optimization method. So here alpha and beta are the beta distribution parameters. Capital F is the CDF of the beta distribution. And lambda is the Gittins index, and gamma is a parameter of the Gittins index. We can vary the gamma value of the gamma from 0 to 1. And if we strictly follow bandit allocation method, there are chances that some cities may get 0 testing kits. To avoid this issue, we take a small fraction of the total number of testing kits, and we allocate the uniformly across all cities initially before going forward with a bandit allocation. And the third component of the testing, the allocation framework, is pooled testing. So if the prevalence is very low, most of the test results will be negative. So that's why the prevalence is very low. So in this case, if we test a group of people together, in pooled testing, we test a group of people together. So the test result will be positive even if there is one person exists in that group. So for COVID-19, it is found that we can go up to 100 persons in a group, and in the sample of 100 persons, 100 people, if at least one person is infected, the sample result will turn as positive. So in pool testing, what we do is that we divide people into groups, and one testing it is allocated to each group. And then we take the positive tested groups and they further divided into smaller groups and tested again. So this is continued until in the final round we allocate testing it for each person who is from the positive tested groups. So this is a visual representation of the polling method. So initially we have larger groups and finally we will have individual level testing. So here we need to find two variables. First one is the how many number of rounds we need to do testing, and the second one is what will be the group size at each round of testing. So this is a difficult problem to solve analytically. So we use simulation method to solve all the problem. So this is the simulation algorithm to find out the variables value. So here we start with a 2-round testing where the first round is the group size 2 and second round is individual level testing. And we increase the group size until we reach a point where increasing group size will not be beneficial. So then at that point we increase the number of testing rounds and we do the process until we reach a point where the maximum number of rounds, we reached an optimal number of rounds and optimal group size for each round. So this is the pooling algorithm we follow, and this is the overview of the allocation framework. So initially we have prevalence estimation method in which we use an empirical Bayesian methodology. We use two methods, beta binomial and gamma Poisson. And in testing with allocation, we use a multi-armed bandit method. And we use two methods of solution, Gittin's index and Thompson sampling. And pool testing, we discussed about the multi-round testing, and we can limit the number of rounds to 2. So the major issue with the pool testing is that if we have to do 5 rounds of testing, we need to collect 5 samples from each person. So it will be very inconvenient to implement practically. So in that case, we can settle for something like a 2 rounds of testing. And there can be, so we are comparing to 3 cases when there is no polling and there is only 2 rounds of testing and there is no limit to number of rounds of testing. So this is the overview of the total allocation algorithm. We estimate the prevalence, and we initially allocate a fraction of testing to each cities, and then we use the multi-armed bandits methods to allocate testing to all cities. And then after doing allocation, we find out the pooled testing schemes. That is the number of rounds and group size at each round of testing. So this is the overview of the allocation algorithm. And to find out the efficiency of the allocation algorithm, the allocation framework, we did some simulation experiments. So to do the simulation experiments, the data is taken from 5 major Indian cities. And we assume that there is only one testing lab at each city. So the relevance of this assumption is that we can do the pooling at a lab level only. Since people come to only one lab at a time, we cannot ask people to come to different labs. So it will be very difficult. So we assume that there is only one testing lab at each city. And as I said earlier, if we strictly follow MAB, it will result in a 0 allocation. So we take a fraction of testing it and we allocate that uniformly beforehand. So the results from the framework is compared against existing numbers. So the actual number of detections and testing numbers are taken, and we compare the output of this method against the actual number. But we cannot say that as we increase testing, we can detect infected people as much as possible. There should be an upper limit to the number of infected people at a time. So this upper limit to the maximum number of detected cases a day is found using a capture-recapture method. It is taken from a paper model written by Boning et al. And the framework, after experimenting the framework with a 5-city dataset, it is validated against a 65-city dataset. So these are all the results from the simulation experiments. As we can see, so there are 10 methods we experimented against the baseline method. So including baseline method, there will be 11 methods. So the latest GP refers to the gamma Poisson prevalence estimation method, and BB refers to the beta binomial Bayesian method, and TS is for Thompson sampling, and GI is for Gittins index. Gittins index is only used with beta binomial only because the index finding equation is only available for beta binomial. But the Thompson sampling can be used along with any Bayesian method, as this is a sampling method. And we experimented with three types of testing, pooled testing schemes. So first one, there is no pooled testing. The last GPTS, BPTS, BBGI methods, and RX means the number of methods of testing is not limited, and after is there is only maximum 2 number of rounds of testing. So as we can see, the multi-armed bandits methods perform very much better than the baseline method. So baseline method provides 48% of detection, where the multi-armed bandit methods provide minimum of 54%. And for the pooled testing, we can see the minimum value we get is 67%, which is very much higher than the actual numbers or the methods without pooled testing. And the difference between the multi-round testing and two-round testing is very low. Like for BBGI method, the 67 and 68, and for BBTS it is 68.24 and 68.45. There is increase in multi-round testing, but it's very slight. And also comparing against Bayesian prevalence method, you can see that the gamma Poisson methods perform better than the beta binomial method. So these are all the results, numerical results we obtained from the simulation experiments. And this is a visual representation of the results. So we can see the bottom line is the baseline method, and the top ones are GPTSRX and GPTSR2. The top values are multi-round and two-round testings of gamma Poisson with the Thompson sampling method, and the middle values are methods with no pooling, but with multi-armed bandits method. So this is for the 5 city data set for 100 days of period. So this starts from 2020 June to 2020 October, and we can see as the number of as the period goes forward, the efficiency is lower. It is mainly because the prevalence, as the number of days increases, more people will get infected, and the prevalence rate will increase. So over the time, the advantage due to the pooled testing will diminish as the prevalence rate is high. And three methods out of these 10 methods, 3 methods are taken and compared for the 65 city data set. Here only we take 20 days data only, and we can see that here also the results are almost same, except that the pooling method, the multi-armed bandit methods without pooling is almost similar to the baseline method. It happens because mainly in 65 city data set, it's very varying in terms of demographic factors like population density and everything. So there is an advantage in multi-armed bandit methods if we don't use pooling, but the advantage is very slight. And if we use pooling, there is obviously better advantages over the time. And over the time, we can also here also the advantages are reducing because the prevalence rate gets increased. Here we only took 20 days data only because of the computation limitations. So based on the development of method and experimental studies, these are the conclusions we have reached. So we developed a framework which can allocate and optimize the utility of the COVID-19 testing kits. And the framework is provides better performance against existing numbers of detected cases. And we already seen the pooled testing always provide great improvements, especially if the prevalence rate is low. So the major reason why people don't use pooled testing is not due to the mathematical reasons, because mainly due to the medical reasons. So if there is no proper medical guidance to do how to do pooled testing, we cannot do pooled testing. So that was the major reason why we don't use pooled testing during COVID-19 and all. And as we see, the two-round pool always provide the advantage of pooling, but it's a very convenient method. As we know, the number of samples need to be collected from each person is fixed. It is 2 only. And the future directions of this research can be on finding out how the resource allocation methods like in this case, the testing it allocation method, how this resource allocation method can provide a how this affect the dynamics of the disease, how this can affect the reduction in the disease spreading dynamics. So these are all the conclusions from the study, and these are all the major references that we used in this study. So the data is taken from the COVID-19 India dataset, and the document paper is where the pool testing method is proposed. It's actually happened very long ago, but people are still not using it. So that's all. Thank you everyone for listening to my talk. And if you have any queries, feel free to ask me.
In case of any queries, please raise your hands. We will take them up one by one. We have a query from Apurv. Apurv, please go ahead.
Good afternoon, everyone. I just wanted to ask, what exactly are these methods that we are talking about, BBGI, BBTS, and so on? What exactly are these?
Okay. So actually, in the slide, so you can see the screen, right? Hello.
Yeah. Yes.
Okay. So that by BB we may denote the beta binomial prevalence estimation method, and by GP we denote the gamma Poisson prevalence estimation method, and by GI we denote the Gittins index testing kit allocation method, and TS is Thompson sampling. And if there is no R digit R letter in the method, it means there is no polling. And R2 refers on there is only 2 rounds of polling, and RX refers there is no limit to the number of rounds of polling. That is, we need to find out the value of the X. So the first two letters denotes to the prevalence estimation methods, and the second two letters denotes to the multi-armed bandits allocation method we used, and third two letters, the last two letters denotes the pooled testing scheme, like how many rounds of polling. And there is no last two letters, that means there is no polling. I hope it is clear.
Yeah, thank you.
Next question is from Sarthak. Sarthak, please go ahead.
Hello, Alfas.
Yes.
You seem to have mentioned 3 methods for multi-armed bandit allocation system, but you used only 2 methods. That is a Thompson and Gittins. Is there any reason behind it? Why didn't you choose a third one?
Okay. So the reason actually there are multiple methods are available. There are other methods also beside these 3 methods. So the reason why we choose only 2 is that all the other methods also gives similar results. Like upper confidence bounds gives same results that of Thompson sampling, and there was other 2 methods like I think it is EXT3, which gives similar results that of Gittins index. So since the methods gives the same results, there is no comparison we need to do. So that's why we only choose 2 methods that give different results.
Okay.
Any other query, anyone? We have with us Professor Bandit. Sir, we would request your comments, suggestions, or feedback.
Well, very interesting presentation. I was just wondering that when you have used simulation, what is the reliability of the results as to how many times the number of runs that you take, etc., whether they are necessary and sufficient. So I was wondering about that one particular part. And the other one is your results that you have drawn from the data. Have you compared it post after the data, what happened as to the results that you obtained and the actual ones that were there. And many times, whether you really had COVID or not, the testing would give positive or negative. Otherwise, how reliable were those tests also? And some people, to get their results done otherwise, they have changed the samples also. So in practice, many of these malpractices have also taken place to show that they are no longer COVID positive. So I don't know how your model might accommodate all those things.
Okay, sir. So the regarding the first question, the number of simulation experiments we conducted. So actually, we did 50 rounds of simulation. So the standard deviation value for here it is shown. So it's the standard deviation value from the simulation results, like the standard deviation of the in the detection rate. So we done 50 simulation runs for each round from each method, and this is the standard deviation value. So we can see that the standard deviation is very low. So that indicates like the results is almost same across all the runs. And regarding the false positives and the manipulation of results, so the one thing I think the advantage is that if we do multiple rounds of testing, there are less chances of manipulating the false positives and or true negatives and all. So because we do multiple rounds of testing, so there are also chances that we may miss people in the first round and they tested negative, but they are actually positive and all. But we cannot do anything on that contest. But in the case of false positive, I think this method is more sufficient because as we test more in different rounds, it will be beneficial to exclude false positive and all. So that's only the idea in this context.
One in the lighter vein, in Kaun Banega Crorepati, one day there was breaking news that Amitabh Bachchan is now COVID positive.
Mm.
And yet we found that the shows kept going on. Now, whether that was a false note or a propaganda note or a way of making it more popular, because he made a statement that all those that came in contact with me should also get tested. So I don't know, on a lighter note, whether your sample or your method can take care of such propaganda also.
So I think it's a administrative level decision. Like actually, we can if we do multiple rounds of testing, but people need to cooperate also. Like that's more of
Yes.
a. I think our method doesn't consider that aspect of the testing and all.
And the probability that if you have it once, you won't have it a second time. And if you go in for the booster, that again, there's no probability. Uh, but apart from this, in terms of practical implications, is there any way out that you can suggest that what would be the probability of really catching on, even if you were twice negative, the third time you become positive or something? It's just a thought, that's all. Maybe I know difficult in the modeling process, but
Well, actually, we can do a Bayesian model in that context also. Like we have seen that the most of the people in India got COVID in the second wave. So in the third wave, it is not very hazardous. Like the symptoms were mild and only a few people got infected. So I think over the time, if we got to one time the second round, it will be less hazardous. So I think if we use a Bayesian modeling, we can estimate that after each number of vaccination or after each number of infections, we will the probability getting reduced and reduced. So I think in that context we can use Bayesian modeling, and I think it is possible to incorporate in this model. So as I said in the last slide, if we can allocate the resource allocation model into a disease dynamics model, we can incorporate such data also, like which people are in the infected and recovered stage, and which people are on the recovered and or recovered or vaccinated states, things like that. So we can allocate different probability of getting infected to different people. So instead of taking a all population level prevalence rate, we can assign different probability of infection to different people. So that's actually mainly part of the disease dynamics models.
Very good. And from where did you get the term bandits coming in?
So
Standard?
yes, it's a standard method. So
Because,
it's
you
a
know, because
yes,
bandit seems to get confused with bandit also.
yes. So it's a classic reinforcement learning problem. It's actually mostly used in medical medical field, because in medical field the data available is very few. We cannot test people to experiment a new method or nothing like that. So instead of going for a completely randomized control trial, we take one case at a time only. We test the method, treatment protocol, or disease or medicine at a person at a time, and then based on the feedback from that person, we go with second person. And if the probability is getting lower, success probability is getting lower and lower, we have to give up the method. But in what do usually happens is that we take a group of people, like around 30 people, and we apply the treatment protocol to them. So in that case, if the success probability is very low, it is very dangerous to those people. So if the data is the data size is very low, or the probability of success is very, or the case scenario where it's very dangerous to the people subjects that go under through the study. In that case, we can use a mostly reinforcement learning model for online decision making methods. So multi-armed bandit methods used mostly in those contexts.
Well, thank you from my side. I hope the actual medical field also recognizes your work and puts it to benefit. I don't know, it may have already been done, but congratulations from my part. Thank you.
Thank you, sir.
We have one more question from Apurva. Apurva, please go ahead.
So I just wanted to ask, I want to understand more about multi-armed bandits and how are they being used here in the simulation.
So okay, so in multi-armed bandits, so the idea is that there is a gambler and there are k number of slot machines. So the slot machines may give, let's say that the slot machines are binary, like whether they give a amount that's greater than the money you put, or they give nothing. So you don't know the probability of getting the bigger sum of money. So what do you do is that, and the probability for different slot machines can be different. So if the probability is same for all machines, the you can estimate an average value what you are going to get. But in this context, the probability of each slot machine is different. You don't know the probability of success at each slot machine. So you put money, instead of you put all the money into one slot machine, you put a small amount of money into each slot machine, and based on the output, like the number of times you get a better amount of money, or the number of times you lose the money, you develop a probability model around that thing. So there is a idea of exploration exploitation. Like you can exploit the machine which gives you maximum output, or you can try other slot machines where they may give you better output. So that is the exploration exploitation. Like we can exploit the available data, or we can explore the unavailable areas. So in this context, instead of slot machines, we have different cities. And instead of the winning probability, we have prevalence rate. So the idea is to whether allocate it to, testing it to places where prevalence is very high, or to consider in the future cases to allocate the cities to where prevalence is very low. So obviously, the chances to getting allocating the testing it to places where prevalence is high is usually like it follows the prevalence rate, but there is a chance of randomness. So this randomness is where the places where the prevalence rate high, low, or in the case of a pure MAB problem where the slot machine that is less explored get a chance. So that's how the multi-armed bandits are used in the context of testing it allocation.
Okay, so MAP is a sort of is it sort of a reinforcement learning technique, or what
Yes,
exactly?
yes.
So that's how
It's actually a reinforcement learning problem, maybe.
okay, and you are basically deciphering the probability distribution of each of those cities of the
Yes, yes,
prevalence rate.
yes, yes.
Thank
And
you.
actually, maybe it's a problem. Like it's not a solution algorithm. It's a type of problem, and the solution strategies are developed over time, and there are different solution strategies available. So we should use two methods: Thompson samplings and Gittins index, to solve the MAB problem for the testing it allocation.
Right. Okay, thank you so much.
Okay, thank you.
Is there any other query? So in case of no further queries, we can end this session now. Thank you, Alfas, for such an informative presentation. And thank you everyone for being a part of this session. Would request the team members to please take.
Thank you, Adya. Thank you. Thanks everyone for the participation and support. Thank you.